Oh, nice. Okay, so I am streaming now. Hey guys, my name is Jonathan Wheeler. I've just set up kind of a studio in my garage that I can use for sharing my screen, making tutorials, making presentations. And what I've got for you today, I'm going to share with you how I use PyTables to record scientific data that I get out from the lab. So this is all going to be using simulated data. So no real data is going up on here, but I'm going to show you kind of the workflow, whether you're a colleague or just another researcher in another group that's interested in duplicating some of the methods that I've been using. So I'm using Jupyter Notebook. It's a way to run Python scripts and prototype them really quickly, and then also share them where other researchers can make tweaks and see how small little blocks of code run. And right now, I've got my keyboard set up for Dvorak. It's another keyboard layout I'm trying. I'm a little slow with it. Sometimes I get a little stuck because I forget where a key is. So if this gets too frustrating, I'll just switch over to another keyboard. But I'm just going to name this notebook. Most of the notebooks that I write, I date with the current date. It just gives me a little bit of context. And actually, I don't have anywhere on my screen where it says the date. Okay, today's the 7th. Okay. This is the 7th, and this is going to be a PyTables demo. Okay, so it's idiomatic in Python at the beginning of every notebook or at the top of a file of a script to put all of your imports at the top. And so here are a couple imports that we're going to be needing. I almost always use, I'm just going to go back to a QWERTY keyboard. I almost always use NumPy. And it's idiomatic to abbreviate that as NP, matplotlib for plotting. We're going to be using PyTables. And I find that date time is useful. Time is useful, and I think that's all we need for now. If we need more, we'll go back and we will add more imports at the top. So like I said, the purpose of today is going to be showing how I record data that comes out of sensors. And what I'm going to simulate here is a sensor that just generates random noise. It's not going to be that useful of a sensor because all it makes is noise, but it will be something that we can code up pretty quickly here. So I'm going to make a data acquisition unit. And when you make classes in Python, you need to have an initialization script. And this DAC is going to take 2 arguments. It's going to have a sampling rate. So that'll be the frequency of sampling. And then it's also going to have a noise amplitude. So I'm going to say this is the RMS. And so self-sampling rate equals sampling rate, and self-RMS equals RMS. And then if we want to read a certain amount of time of data, we're going to call this function read. And read is going to take as an argument the time, or the duration of data that we want to read. So the number of points is going to be rounding down the duration times the sampling rate. And we're going to return an array of random variables. And they're going to be, it's going to be of length num points. And the amplitude is going to be RMS. So I'm going to just test it really quickly. I'm going to initialize a DAC, and the sampling rate is going to be 10 Hertz, and the RMS value is going to be 5. And if we read something off of this DAC, let's take, okay, so if our sampling rate is 10 seconds, we sample for 5 seconds, we should get 50 seconds worth of data. This didn't work because it's not referencing the internally saved values. Okay, and that looks about 50 seconds of data. And if we try to get the standard deviation of this, it should be close to why is that not? Let's see, this should be, oh, here we go, that's the problem. Now it should be returning a Gaussian random variable. Yep, and now the variance, okay. So now, yeah, the standard deviation of this is the same as the standard deviation that we put here. And we can just be a little bit more, there we go. So yeah, we can get out whatever data we need from our little simulated DAC using this little command here, and this will give us 100 seconds of data. Okay, so next I'm going to create a file that we can use to capture this data as our script reads it in. So to do that, I'm going to make a variable called h5file, and it's going to be opening a new file. I'm going to call it 2020 1007. I'm going to call this demo. And we need to have write privileges, so we'll put a W there. And so now we have, if we just put this here, we have a HDF5 file here that's linking to, you know, this file name. And there's a couple other things here that show, you know, the compression level, et cetera, et cetera, et cetera. Most of those are unimportant. And what we're going to do is we're going to create a table inside of this file. PyTables works by implementing the same file structure that MATLAB uses to save files. It's kind of think of it as a zip file that has folders and files inside of it. Each of the files is an array of or a table of information. In each of those files, you can attach metadata to them. And then each of the folders also can contain other folders or other files with metadata that you can attach to them. And so this H5 file, all it has right now is just a root folder that has no children in it. And we can change that. We can say, let's take this H5 file and create a table. And we're going to create it at the root. And we're going to need to give it some title. So we can say here, for this case, we'll just be reading detector noise. And then we need to give it some sort of a description. And I find the easiest way to give this a description is to create a class that extends PyTables is description type. And so what we're going to put in here is just the different columns in the table that we're going to need. And so this is kind of a simple mock example. So we're going to want a timestamp. And this will be a time 64 call. And we're going to want, let's say, a voltage. And this is going to be float 32 call. The 64 and the 32 here tell you how many bits of information each row or each entry in here is going to take up. You would put a 32 here if you were just wanting integer timestamps. But in this case, because we're sampling faster than once per second, in this case we're sampling at 10 hertz, that means that 10 values would have the same timestamp, and we want to have finer resolution. So we would do that with a 64-bit timestamp. And for the voltage, in this case, 32 bits will be all that we need. If you're doing very fine measurements where you have very, very, very small changes, basically where the value is going to have the same first like 5, 6 numbers being the same, but then the last one is changing just a little bit, then you would probably want finer resolution with a 64 call. And that's probably all I'll say about that for now. So we have, this is our table description, and so I'll just put this here, description. It's the same name as we have here, and we'll assign this to a variable called table detector noise. Great. So now we have table detector noise. And you can see that there's no data in it yet, but it has a timestamp column, it has a voltage column, and then these sorts of things are basically just low-level things. In normal situations, you're not going to need to know anything about this. So now we're going to actually, so this would be everything you do to set up your experiment, and now you're going to take data. So I'm going to, in real life, you might sit here and take, several different measurements over and over again. So I'm going to create a for loop. I'm going to say for dummy variable in range 10. And I'm going to grab, let's say, 5 seconds of data. So this data variable will now hold 5 seconds of data off the DAC. And then what I need to do is to create rows of data, or new rows in this table to fill. So to do that, I'm going to ask for row equals table detector noise row. And I'm going to have each row, the voltage, be this new data value. Now, what I really should be doing, because data is going to be a list of, in this case, 5 times 10 hertz, so 50 points, I'm going to say for data value in data. And so I'm going to create a new row for every bit in this, every element in this array. And then I'm going to need to assign a timestamp. And the way that I'm going to assign a timestamp, I'm going to have the timestamp at which we started, initial timestamp equals time.time. And every time I enter something into this timestamp, I'm going to put the last one here, last time. And so I should probably put last time initial timestamp here. And then I'm just going to increment 1 over fs. And I guess the fs here is currently stored in the DAC. In an actual implementation here, you might be storing this somewhere else. It might be some sort of a global parameter. Maybe you have some dictionary up here that has a bunch of other information about your experiment. But we're just going to increment the last time, and so every time you come back here in the loop, this will increment a little bit, and you'll have another row, or a new updated timestamp. So if we do this, we are getting 50 samples every time we run this, and we're doing it 50 times. And so this will create about, let's see here, 500 rows into our table. There's a few more things that we need to do before we actually run this. At the end of each loop, of this inner loop, we need to append the row to the table. This basically tells the program that we are done writing to that row. And then it's also a good idea to periodically flush your data to the disk. What PyTables does for performance issue reasons is that it will cache everything locally and then wait to flush it to the disk, so that way once you've done all your bookkeeping, then it writes, rather than writing every single time you change a small little piece of the table. So this should be ready, and it should run. Table's not defined. That's right. It's because this is called table detector noise. There we go. And now if we look at this now, okay, yeah, we have 550, and that's because I accidentally ran 50 rows the first time. Let me just restart and run everything just to clear that up so it's truly 500 so the data is contiguous. All right, there we go. So now, if we want to read the data back, I'll make a new section here, reading back the data. We have table detector noise. And if we want to get the timestamps from here, call timestamp. And if we want to get the voltages, we can go table detector noise, call voltage. And now we have these two here, and we can plot them. And then there's your data right there. One thing that I like to do with timestamp data is I actually like to convert it into a format that NumPy knows natively what to do with it. And the way that I do that is that I'm going to convert these. Right now, these are all listed as seconds since the epoch, which was back in 1970, January 1st. So I'm going to convert this to nanoseconds since the epoch by multiplying it by 1 billion. And then I'm going to go as type date times 64 nanoseconds. So now when I plot this, there we go. And as I'm recording this, it's 4:26 in the afternoon. So you can see that we simulated roughly 50 seconds of data. So, you know, we did this five seconds of data 10 times. So that's 50 seconds. And so from here to here is about 50 seconds across here. And you can see your voltage here. So, you know, if you wanted to complete this graph, you could have a label saying that this is your voltage. And what I'm doing now, it's usually good practice to put down the units, which are also associated here. And while I might know, because this measurement is, you know, fresh in my mind, that I had so many, like for example, this might be millivolts. If somebody were to come back to this in a year, they wouldn't know whether it was millivolts or volts. So for now, I'll just put this down here. But it would be a good idea for me to record somewhere that this y-axis data is recorded in millivolts. And the way that we do that is we go table detector noise, and then we can access the attributes here. So for example, we have, you know, this is some overhead related to PyTables. It's telling that this is node as a table, and it's saying that field 0, when you create a new row, fill it with zeros. Field 0 is the timestamps. So it has all this information in it. So what I'm going to do is next to, and this is just something I personally do, the exact style that you do this, you can do it however you like, but I want to have a field 1 fill, I have a field 1 name, so I'm going to make a field 1 unit. So I'm going to go field 1 unit, and I'm going to set it to millivolt. So if I come back to this experiment, this file, like a year from now, and I want to see what was there, then I just know that it's this. Yeah, and I could even do, and just embed it programmatically here if I wanted to. And there you still see it has the millivolts there. So this is kind of a high-level overview of how I use PyTables. It's a really great format. For example, if you were to want to set up a second experiment and save it side by side in the same file, you could create another, you know, another table where you could have a new instrument. Let's say that this is, you're comparing two different detectors, and you got a new one, and you want to see if it's better or not. Let's say it actually is better. So this could be table for the new detector, right? New detector noise. It will have the same description. It's at the same root of the same file. And let's say we decide to run this one 20 times. this is all just sample stuff. You guys can adapt to your own purposes. Make sure that it's the same everywhere. And then if you wanted to compare this one, we can plot both of them side by side. For table and table detector noise, table new detector noise, so yeah, you can see this is the results of the first test, and we can, let me just quick get the current figure, G get current figure, and then auto format the X dates. There we go. So you can see that our first test was run starting at around 4:26, and then it finished 50 seconds later. And you can see our second test, we started a little bit later, and it's over here, and we were able to just iterate between the two different tables. They had the exact same data format, and so they're very easy to compare side by side. So thanks guys for watching. I hope that you got something out of this. Let me know in the comments if you find these helpful or not, if you have any questions.